Welcome to Lesson 4E, Isentropic Converging-Diverging Nozzle Example. In this lesson, we'll work through a detailed example of isentropic compressible flow through a CD nozzle when the back pressure is low enough that there's no shock in the nozzle. And we'll calculate and plot Mach number and pressure throughout the nozzle and compare our theoretical results with those calculated by CFD. I start with a review of the isentropic equations for temperature, pressure, density, and the area ratio versus Mach number relationship. These are all restricted to ideal gases, of course. This area ratio relationship, as you should recall, has two roots, a subsonic root and a supersonic root. For our typical converging-diverging nozzle, recall from previous lessons, or case E, had a shock at the exit plane. Well, here we'll discuss the case where PB is less than PE. Therefore, the entire nozzle is choked with no shock in the nozzle. Therefore, the isentropic approximation is reasonable. We'll see in our example problem that we have to verify this. And for this case, under these conditions, there's no shock throughout the entire duct. The throat is what we call A star. We have upstream stagnation pressure and stagnation temperature in the large tank driving the flow. And as you recall, in the converging section, the flow is subsonic, and in the diverging section, the flow is supersonic. But for some arbitrary area in the duct, there are two locations where A over A star is the same. So we must be careful to choose the subsonic route in the converging section and the supersonic route in the diverging section. And when you're doing these kind of problems in software like Excel or MATLAB, you have to be sure to choose the proper route depending on where you are in the duct. Now I'll do a detailed example problem where air flows from a very large tank, as shown, through a converging-diverging nozzle, and we pick x equals 0 at this somewhat arbitrary location, and then the length of the duct is 0.60 meters. The back pressure is 50 kPa in the air outside of the duct. I give the stagnation pressure and stagnation temperature in the upstream tank, and I show a table here of the area versus x. As you can see, area decreases till we hit the throat, and then starts increasing again until we get to the outlet, as is also sketched here. We assume isentropic flow, which requires there to be no shocks, since flow across a shock is not isentropic. And then we'll calculate and plot Mach number and P over P naught as functions of x. Then we'll calculate the average airspeed at the throat and the exit plane and m dot through the CD nozzle. And to be consistent with my notation, it should be C-D. We make our standard approximations: air with gamma equal 1.40, steady 1D, adiabatic, and isentropic. And we can calculate PB over P naught as 0.2273. We assume this is low enough so that the flow is supersonic through the entire diverging section of the nozzle, as we just discussed, meaning there are no normal shocks in the nozzle. But we will need to verify this assumption. Let's do some sample calculations, and I picked x equals 0.40 meters as our sample point. From the table we can calculate A over A star. Since we know A and we know A star, I get 1.33587. Now we use the area ratio versus Mach number relationship, where we choose the supersonic route, since this location at 0.4 meters is past the throat and is in the diverging portion of the duct. Well, we solve for m, picking the supersonic route. Again, this is implicit, so use whatever software you would like. I get Mach number is 1.69815, the supersonic route. Then use our isentropic pressure ratio relationship with this Mach number to get P over P naught as 0.20316. And then we multiply by P naught to get the pressure at this point. To 3 digits I get 44.7 kPa. Now we repeat these calculations for all x locations in the table. I used Excel, and I'll show my results here. These are our calculations from our isentropic equations, the theory, and I will compare them to CFD results. Notice how Mach number increases to 1 at the throat and then keeps increasing supersonically to the exit plane, or outlet. Our sample calculations were at x equals 0.4, and these values of Mach number and P over P naught agree with what we calculated by hand. I ran a steady CFD simulation of this flow as indicated by the circles and compared them with theory as indicated by the lines.
Well, I never knew you could use CFD for compressible flow.
Well, Dud, you can, but unlike incompressible flow, CFD requires mass, momentum, and energy equations, and an equation of state, which I chose ideal gas, and I used ANSYS Fluent for these calculations. The agreement is excellent, as you can see here, but in the table you can see some differences. I also show a contour plot of Mach number, blue being a low Mach number and red being a high Mach number, and I highlight the sonic line, which here really should be called a sonic curve since it's not a line, and it's the locus of locations where the Mach number is 1. It's an iso Mach number line, as are all these other lines here in this colored contour plot. This particular one has m equal 1. One difference you may note from the theory is that this sonic line is not straight, but rather curved. In fact, none of these iso Mach number lines are straight. So the one-dimensional approximation, while reasonable, is not perfect. And I'll comment here that I use the average of Mach number at any cross-section, in other words, at any x value. The non-one-dimensionality explains some of the differences that we see in the table, and that's because the flow is not exactly one-dimensional. Well, we're not done yet, because we need to verify that our PB is small enough for isentropic flow through the entire nozzle. How do we do that? Well, at the exit plane, which in our case is at x equals 0.6 meters, as you can see on the table, PE over P naught is 0.061487. Therefore, PE, the pressure at the exit plane, is this ratio times P naught, which was 220 kPa, which gives us 13.5271 kPa. This value is what we called in our previous lessons PF. In other words, the case of ideal expansion with a nice straight jet coming out. But we have a problem. Our PB is 50.0 kPa. In other words, PB is greater than our PE. So this is not ideal expansion. So we ask ourselves, is our assumption that the pressure is low enough wrong? The answer is not necessarily, because there could be a shock right at the exit plane where this pressure would suddenly jump up, and it might go higher than this PB value, which would make our assumptions okay. To understand this, I'll quickly sketch our P over P naught plot for a converging-diverging nozzle, which you should recall looked something like this, where we had subsonic flow upstream of the throat, a subsonic branch to a pressure that we called PC, case C, and a supersonic branch, where PB is what we called PF, case F, which is our ideal expansion case. But in between C and F, we have cases that we call D, where we have a shock in the nozzle, and as we discussed, as PB decreases, the shock moves down the duct until it reaches case E, where there's a shock right at the exit plane. And when PB is less than PE, you get an overexpanded jet, where you can imagine this shock moving out of the duct. And the reason why I say our assumption is not necessarily wrong is because we could be at case E or a little beyond it, namely, as long as PB is below PE, we indeed have no shock in the duct, which is what we assumed. And by the way, here we had calculated that PF was 13.521 kPa, and our PB is 50.0 kPa. So we know we're above PF, but are we below PE? This is the worst case scenario where we have this shock at the exit plane, but all our calculations up till that point would still be valid. So we need to check if PB is less than PE. How do we do that? Well, again, for case E, The shock is right at the exit plane, where the flow goes from supersonic to subsonic across the shock, and pressure rises from P1 to P2, where our notation is typically that 1 is before the shock and 2 is after the shock. So we'll call this M1 and M2. Well, we know M1 and P1, so we should be able to predict what P2 is, and then compare that with our known PB. But how do we calculate M2 and P2 across the shock? Well, we'll discuss shocks later in the course, and I'll show you the equations we use. For now, we'll use the compressible aerodynamics calculator, which I showed you previously online. I'll scroll down to the normal shock relations. Gamma of 1.4 is for air, so that's good. And we plug in M1 as 2.4683, which is the value we got from our table, and hit calculate. This gives us the subsonic Mach number downstream, 0.516 something. And what we're really interested in is P1 over P2, which is 6.9413. Notice that the pressure jumps by almost a factor of 7. So from the calculator, for this shock at the exit plane, P2 over P1 is 6.94126, from which P2 is P2 over P1 times P1, using the ratio we got from the calculator and the value of P1 that we calculated in our analysis. We get 93.89 kPa, which is what we've called PE, the pressure just downstream of a shock at the exit plane, or P2 on the compressible aerodynamics calculator. Finally, since our PB is in the range between PF and PE, where we recall our PB is 50.0 kPa, we can therefore conclude that our assumption of low enough back pressure is valid. Now let's do part B of our problem, which was to calculate V at the throat and at the exit plane and the mass flow rate. I'll show my solution. At the throat, we know that M equal 1 since this flow is choked. M equal V over A by definition, so V equal M times A. A equals square root of gamma RT, so we need T. We'll let T equal T over T naught times T naught, where from our isentropic relationship, T over T naught is 1 plus gamma minus 1 over 2, Mach number squared to the negative 1, and we'll set M equal 1 at the throat. And T naught was given in the problem statement, namely 300 K. Plugging all this in and doing the algebra, the speed at the throat equal A, the speed of sound, which turns out to be 316.94 meters per second. Now consider m dot. Since the flow is choked, we know that m dot is m dot max, and we can use the same equation for m dot max that we had derived for a converging nozzle. Namely, m dot max is p naught a star square root of gamma over RT naught, gamma plus 1 over 2 to the exponent negative gamma plus 1 over 2 gamma minus 1, which you can find on the equation sheet or in some previous lessons. Or m dot is rho VA at the throat, where we now know V and we know A, which is A star, and we can easily calculate rho from the isentropic equations. I checked both of these, and they both give the same answer. Namely, m dot is 9.0722 kilogram per second, which I report to 3 significant digits here. And as I've said previously, it's always good to compare 2 different methods and hope you get the same answer. Finally, let's calculate V at the exit plane, which we'll call V sub E, E for exit. From our table of calculations that I did in Excel, at the exit plane, ME is 2.4683, PF, the ideal expansion case, was 13.5271 kPa, and our PB is 50.0 kPa, which as we've said is greater than PF. As I've mentioned before, since our PB is in the range between PF and P capital E, this is an overexpanded CD nozzle, which from previous lessons is the one where the jet is pushed in by the back pressure, since PB is greater than the ideal expansion case. and we get shock diamonds and other interesting effects down here. But in the entire duct, there are no shocks. So at our exit plane, the flow doesn't really care what's happening down here. We know our Mach number, and this flow can be approximated as isentropic in the entire duct. Therefore, we can use our isentropic ratio equations to calculate temperature, speed of sound, etc. at the exit plane. Namely, TE is TE over T naught times T naught, and TE over T naught comes from our isentropic relation, and you can verify that this turns out to be 135.226 K. From this, the speed of sound at the exit plane is square root of gamma R TE, which you can work out to be 233.097 meters per second. And then finally, VE is ME times AE. And we plug in this ME, and I get 575.35 meters per second, which to 3 digits is my final answer. I'll quickly mention an alternate method. Since we calculated m dot, and m dot is rho VA anywhere, it's also rho VA at the exit plane. And we know that rho E is rho E over rho naught times rho naught. And we use the ideal gas law to find rho naught, and we use the isentropic relationship for density to find rho E over rho naught. And then taking these and solving for VE, where we also know AE from our table, we also get 575 meters per second. And as always, I'm very happy when we have this kind of agreement. I encourage students to work out all of the details that I left out in some of these calculations and make sure you can get my numbers.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.
1, 2, 3.